before like 9 to.
I know the board opening.
I can't.
Like I would.
No, I totally forgot about
This
it.
is the best chess player in the world played 10 games without looking at the rules, just from hearing like on each.
Oh, yeah, people
He kept track of all that.
Yeah, they have that.
People,
Like,
like,
people like read chess.
Yeah.
I don't know how they do it. It sounds so
This
boring.
dude's
Like, that's the most boring thing I've ever heard, reading a chess game.
Or you can watch skins. That's pretty lame too.
Is that the equivalent?
Yeah, it's just right block, jump, shoot.
Wait, what? Oh, I thought you said.
Oh,
It's kind of long. Right block.
yeah.
That's open. I would go for that block.
No, right block is, that's like.
No, I don't get there that much anymore. I kind of just, I think I've ever called it for videos. Like I'll do one crossover and then jump like. 50.
Yeah, it's like.
Oh,
Will
you-
Were you?
And I just- I just-
Yes.
You shoot your number. That's the any.
You kick them forward and fall backwards.
Were you just hit
Easy game.
Where you just elbow people in the ribs.
Will thinks it improves his shot when he goes like this.
Definitely does.
Nose inward.
Which pigeon toes?
Those inward.
That's a strategy.
Yeah. You see like all the best players do.
They don't go.
They just don't do that.
They do have their feet pointed away from the basketball. Which
It's usually straight.
yeah, you look at it,
It's definitely straight.
Wow, it's just here. It's right there.
look at this.
Hey, you come try this, man. You do three.
We'll pull up just like, all right, James Harden. Shooting 4. Boom.
It's hard.
Is doing James Harden?
Why?
He was getting wet. It's yeah.
He has like three, 4.
It takes too long to shoot.
Okay, who's the one person that's just like wet, but it's just terrible? Like, they shoot like that.
No,
Someone's
someone's
just
shooting
like-
like
yeah,
this.
someone's pretty bad.
It's a laser.
But he's funny.
Yeah,
He's so good. He was really good.
Who?
yeah. He was
So
just fine.
long. And kind of too long. That's what I was saying. That dude. Too high.
Inborn, he's like trying to get the ball for.
Or shooting the free throws.
A horse for the from the church just kind of worth.
Or
He
just
doesn't
like-
say so.
It's so bad, the definition of terrible.
He's so unorthodox.
It usually doesn't.
Yeah.
Why are there all of a sudden bells? There weren't bells the first 2
Yeah,
minutes.
that's
No. There wasn't a belt to even like.
That was the first bell today.
Yeah. I don't understand. All right. We are on lesson number 31 out of 35. So getting really close to finishing. Next week we'll be finished with lessons. Following week we'll be finished with last tests. And then we'll just have our little last project to do and then we'll be done. Tomorrow and Thursday are early release days where you have half your classes for basically a full period. So just don't forget to look at the schedule tomorrow. So you don't show up late or early or whatever to your classes. And you'll only have your first 4 tomorrow and then the next 4 the next day. So yeah. All right, we have our, I guess, 4th to last lesson, which is on what's called linear programming. So kind of like I mentioned yesterday, we'll do very simplistic examples of some of these application problems. And most of them would involve like entire courses based on how you would do these for kind of like more complex problems. But this kind of gives you an idea of how this works. Linear programming is basically the way of maximizing or minimizing a linear function. Linear functions just meaning variables to a first power, but there could be as many variables as you want. It's just that none of them would be like squared or cubed or something like that. So similar to what we did in calculus, only this would become very difficult in calculus to do with lots of variables, or we did it with 2 variables and 3 variables, but once you get larger than that, that would become a pretty complex calculus problem. Linear programming is not really get super complex. Like everything else in linear algebra, it becomes a lengthy problem, but not really more difficult the kind of the larger it gets. So basically what we'll have is we'll have a matrix A, and then we'll have vectors B and C. A will be short and wide, meaning more columns than rows, because that's usually how we're going to end up with late people. All right, that's how we'll end up with lots of possible solutions. We're trying to find a maximum or a minimum. And so usually what we'll have is what we call constraints, which will be given by.
Whoever's breathing into their mic, can you stop breathing in your mic?
What did he say?
Someone's breathing loudly into their mic. I don't hear it. But
No, because when that happens, you like can't hear who's actually speaking. That overrides it.
weird. All right, so we'll have constraints AX equals B. So basically all of your equations you'll put as rows of A, the coefficients, times X equals B, and you'll kind of put all of your equations in there. A will be M by N, X will be N by 1, and B will be M by 1, just like what we've been doing this whole semester. So B will have M components. C will have N components, because ultimately what we're doing is we're minimizing or maximizing C dot X. I do hear something clicking. Okay, well, I don't know. I don't see anyone else unmuted. I mean, could be this. No, I don't think that's even. All right. So yeah, we're gonna minimize or maximize C dot X. So since X has N components, we're gonna take a dot product with C. C also has that N components. And so when we multiply here, this will just be, C1, C1x1 plus C2x2, whatever. That our cost is multiplied by our, you have these coefficients multiplied by our unknowns. Typically, our unknowns are all greater than or equal to 0, because they almost, the whole purpose of this is be some sort of a context where you're maximizing or minimizing something. Usually it's cost, which is why it's a C, but it could be all sorts of things. So typically X is representing an actual kind of thing, like you're selling something or you're buying something, or it could even be time, but usually in context, it makes no sense for those X's to be negative. So pretty much that's always part of your constraints as well. So we're kind of looking at non-negative unknowns in all these problems. Okay, so basically what we'd be looking to do is pick the solution that minimizes cost or maximizes something if you'd rather. It's the same process for maximizing. These shouldn't be vectors, but basically your cost will be given by C1x1 plus C2x2 plus C3x3 and so on. And then have some sort of constraints on those variables given by your matrix equation AX equals B. And we'll just do very simple problems with this. So for example, say we wanted to minimize 5x1 plus 3x2 plus 8x3. That would be kind of our cost equation, or our C. Making sure that x1 plus x2 plus 2x3 is 4, and that all of our unknowns are non-negative. This part would be the constraints. And would be the part we'd put in the matrix. So 1, 1, 2 times x gives me 4. If you had more equations in your constraints, you would add rows into that matrix. So if we had another one, we'd put another row, and then we'd have another element, which is really, you'd add rows there if you had more of them. And then the way we kind of start thinking about where this is going to occur, this thing is a plane, right? If we think really like x plus y plus, 2, z equals 4, that's a plane. So if we think of kind of the constraints as existing on a plane, all my unknowns have to fall on this same plane together. And again, it could be a 4-dimensional, 5-dimensional, 6-dimensional plane. We could have more variables, but think it'll all be kind of on this plane together. So if we kind of graph that plane, this is the plane x plus y plus 2z equals 4. That's this green plane here. And then if you take the other one into account, that all of the unknowns have to be positive, our choices lie on this triangle right here, okay, above the first quadrant where x, y, and z, or in this case, x1, x2, x3 are all positive. Over here, you'd have negative y's, or no, I guess this is the x-axis, sorry. You have negative x's back here. You'd have negative y's over here. You'd have negative z's down here. But in this one little triangle, those are all the places that satisfy the constraints, which means those are all the possible costs we could have, would be from points in this triangle. Okay, this is called our feasible set, meaning this is basically all of our choices would come from that triangle section of the plane. This, so far, none of this is the cost. This is just what is the relationship between x1, x2, x3 that's possible. It's only the things in or actually on the edge of the triangle also work, since we just greater than or equal to 0. Okay, so all we do is we think of the cost as a plane as well, where we could just set it equal to whatever we want. So like we could set it equal to 0. And that would contain the vectors with 0 cost. Generally, 0 cost is not something that's attainable. We then take that plane and we just kind of increase this number. And we get a bunch of parallel planes going up and up and up, just shifting that plane up. So we picture like there could be a cost plane down here. And we just increase the cost until the plane of the cost intersects with that triangle. Okay, so we would like have a cost low, and then we just kind of go up and up and up and up until our cost plane intersects the triangle where our possible locations would be. Okay, the minimum cost is where it would first touch, right? If I'm starting below and I kind of move up and up and up until I'm first touching the triangle, that would be the lowest cost that would be in my feasible set. And there's really no way to get to like the interior of the triangle without hitting a corner first. So as we do this, we will always touch a corner first, which means the corners are our possible locations for minimums and really for maximums as well. So think this is very similar to the candidates test from calculus. We're just going to identify the corners because the corners are the locations where you'll either hit your max or your min. Because if we took that plane and we just kind of shift it up until we touch, we're going to hit a corner first. We could hit on the whole edge, but that's going to also be a corner, 2 corners and an edge. But you'll always hit a corner first. There's no way to get with linear graphs. There's no way to get to the interior of the triangle without first hitting the edge of the triangle, the corner of the triangle. So basically, we would just identify the corners. If all we have is one constraint, the corners are easy. Think if we were to find particular solutions for the matrix like 1, 1, 2, we would identify like 3 variables, set them equal to 0, find what the other variables would have to be. Basically, as long as I have one equation, I set any two variables equal to 0 and find the third. That'll be a corner. Set the other two equal to 0, find the third, set the other two equal to 0, find the third, and that would be my three corners of my triangle. If I add equations, I can't just set them all equal to 0. Okay, I could set some of them equal to 0. You basically, the number of free variables you have, that's how many you could set equal to 0 and solve for the others to get the corners. So we'll do one with more than one equation in a second. Then I would just check, see which is the smallest. So I get 4, 0, 0. Plug that into the cost equation, and we'll have 20. 0, 4, 0. Plug that into cost, and we have 12. 0, 0, 2. Plug that into cost, and we get 16. So this is our minimum. If we were looking for the max, this actually is the max, the largest number. The other one just in between. There's one corner where you'll have already hit a corner, you'll pass a corner, and then you can keep going through more of the triangle as we kind of raise that cost plane, shift it up. So the lowest value you get is the minimum, the highest value you get the maximum, and then you might get other values in between. Those are neither, and it doesn't, they don't matter in this context. Okay, so really easy if you have one constraint, but this makes a pretty simplistic problem. Most things that you would kind of encounter don't have just the one. You have a lot of things kind of you're having to take into account when you're doing this. But we could give this context, and in general, there would be some context. There'd be a point to this. If you wanted to maximize rather than minimize, just picture instead of starting the cost below and raising the cost until you're in that triangle, start the cost above and decrease the cost until you're in that triangle. It would also hit a corner first. So it will still be one of the corners. So if we wanted to maximize, you do the exact same thing. You just pick the largest number that you get instead of the smallest. Okay, if you can't satisfy the constraints, the feasible set is said to be empty. So say I graphed my plane and it looks like this, but I also need all my x's to be positive. Well, then it should be up here. My feasible set should be above the first quadrant. This plane doesn't have any values above the first quadrant, so this feasible set would be called empty. Basically, there is no way to even get costs from this that would satisfy the conditions you needed to satisfy. So it's possible that you could have that happen as well. I think in general, ours all will have some solution, but it's possible that if you've got all this conditions together and you try to find a solution, there is none. That would be called an empty set. Okay, so for that first one, say we wanted some context, it would be something very simplistic. So say X1, X2, and X3 represent hours worked by a PhD, a student, and a machine. Okay, that all three of these people / this machine can work problems. The cost per hour for work done would be $5 for the PhD per hour, $3 for the student, $8 to run the machine. Okay, and then a PhD student can work one problem per hour. The student can also work one problem per hour. The machine can do two. Okay, that would lead us to that set of equations that we just looked at, where if X1, X2, and X3 represent the hours worked by a PhD, in 1 hour, the PhD would do one, the student would do one, the machine would do two, and I'd end up with 4 problems done after 1 hour if everyone's working. The cost of that would be $5 for that hour worked by the PhD, $3 for the hour worked by the student, and then $8 for the hour worked by, well, let's call that cost. And so our corners would be the PhD solved all the problems, the student solved all the problems, or the machine solved all the problems. And one of those things is going to be the cheapest, one of those things is going to be the most expensive. And then if I let a combination happen, then those things will come out in between. So if we want to solve 4 problems, the PhD would work for 4 hours and charge $20. The student would work for 4 hours and charge $12. The machine would only have to work for 2 hours because it can do 2 per hour, which would cost 16. And so the student would be the cheapest, the PhD would be the most expensive, and the machine would be in between the other 2. Okay, so it'd have to be really kind of simplistic for that to happen. Generally, you have a lot in a real world problem, you would have lots of constraints, lots of variables, and lots of things going on. So if the number of equations increases, and by equations, I mean like in your constraints, we had 1, that x1 plus x2 plus 2x3 is equal to 4. If you have more of those, then each corner will have m non-zero components, m being the number of rows. We had 1 row. So each of our corners was at something 0, 0, or 0 something 0, or 0, 0 something. If I add an equation, I will have corners that are at something something 0, something 0 something, and 0 something something. I'll have 2 non-zeros at my corners. So for everything I add, every row I add to those constraints, I'll have more non-zero components in the corners. I'll also have more corners. As I add things like rows and variables, I'll end up with more corners. It's like for ours, we had 3 corners, a nice little triangle. If I had like 20 unknowns and 8 equations, which is not like a crazy amount for a real world scenario, that would give you 5 billion corners, which this would not be a great method. You're not going to sit there and find 5 billion corners and sit there and plug in 5 billion corners to different costs and try and figure out which is biggest. Not great. Okay, there's a method called the simplex method. We're not going to do the whole simplex method, but we're going to do kind of what it's kind of based on. So we're going to do something very similar. That way, if you see the simplex method, it's built on this idea that we're going to look at now. So if I add complexity to my situation, I still would start by just choosing a corner and checking the cost. And then say, I have this feasible set that has all these corners, and I just pick one and I check the cost at that corner. Then I just start to see, what if I raise a certain variable and lower another one? Or raise a certain one and lower another one, or whatever. And I start seeing what would happen to cost as I head away from the corner I'm at. If the cost starts increasing, I stop going that way. So like I just see what happens if I head that way, cost went up, stop. What happens if I head that way, cost went up, stop. What happens if I went that way, cost went down, head all the way over to that corner. Okay, and that way you can kind of narrow down and start to say, well, I don't really want to move that way because that direction, the cost starts going up. But if I move that way, it went down. So then I know it's at the corner, so I go all the way to the opposite corner that's in that direction. Okay, and the simplex method narrows it down faster, but this is kind of along the process of what you'd be looking at, is you just kind of start to think, what if I start altering the variables from this corner and I leave some alone and just kind of mess with 2 of them. Take this one up and down, cost went up. This one up and down, cost went up. This one up and down, cost went down. So then I want to kind of go full to the opposite corner there. So for example, say we had our cost equation now has an extra variable, and our constraints now have an extra row. So I've got more corners that I could check. And again, you could just find all the corners. This one still isn't that bad. My constraints would be 1, 0, 2, 1, and 0, 1, 1, negative 1 times x equals 4, 2. And so think when we were doing free variables and all that stuff, I'm going to have 2 free variables. So basically, every corner is going to have 2 zeros in it. Okay, or here I have 2 equations. You're going to have 2 non-zero numbers at every corner. So for example, we could start when x3 and x4 are both 0, kind of like when we found the particular solution. We set the free variables both equal to 0, and then use our constraints to figure out what the other ones would be. So if x3 and x4 are both 0, x2 would have to be 2, and x1 would have to be 4. So I'd have the point 4, 2, 0, 0. This is one corner of that feasible set. I could also have done like x1 and x2 are 0, or x1 and x3 are 0, or x1 and x4 are 0, or x2 and x3, or x2 and x4. Those would be my other corners, is setting those other ones equal to 0. So then I just find the costs there. So plug that into my cost, and I have 12 plus 2 is 14. Okay, then I would take one of your variables you set equal to 0 and just increase it. Leave the other one alone. You don't want to increase both because you're trying to find what would be making the cost go up or down. And then use your equations to find the other 2 variables. So if x3 was 1 and x4 was 0, x2 would also be 1. And x1 would be 2. So notice x1 went down, x2 went down, x3 went up. Okay, and so you're kind of trying to keep an idea of what's changing here as I kind of move in that direction. Cost is 6 plus 1 plus 9 is 16. Okay, cost went up. Basically, don't go that way. So we don't want to head in that direction. If I went towards the corners that are that direction on this 4-dimensional shape, the cost is going up as I head that way. So go back and take x3 back down to 0 and see what happened if we increased x4. Okay, and if you kind of look at the cost, you would have an idea of which ones you probably should go up and down, because like x3 and x1 being large are what makes the cost really high. So that's a good also place to probably figure that out. But again, if it got super complicated, that might not be so easy to see. But if x3 was 0 and x4 was 1, x2 would be 3, and x1 would also be 3. And so we'd be at 3, 3, 0, 1. I look at my cost, and that's 9 plus 3 is 12 plus 1 is 13. So this time cost went down. And when I say that, I mean compared to where I was in the corner. These last 2, we're not on corners anymore. It's like we started in a corner and we just kind of moved in different directions from that corner in the feasible set. We're not in a corner, but notice we moved away from a corner and the cost is going down, which means I kind of want to move to the extreme in that direction. So notice when I went that direction, x3 stayed 0, x4 went up, x2 went up, and x1 went down. So I kind of want to move to the corner where x1 and x3 are 0. Since x1 going down decreased the cost, move to that corner where x3 and x1 are both 0. That's another corner. Again, the 2 in between, those were not corners. Corners will be at where 2 of the variables are 0 and 2 are not. So I'd set x3 and x1 equal to 0 since increasing. Oops. No, I wanted to increase x1. Sorry, not x1. What decreased here? X2 decreased. Sorry. Yeah, x2, notice went No, I was right. I'm looking at the wrong one. X1 decreased 4 to 3. So I'm going to set those ones equal to 0. Sorry, I looked at the wrong row. So when I'm saying that, I wanted to see X1 went down. X3 was already down. But these two variables increased. I'm just drawing arrows to the wrong things. It's cool. This one increased, this one increased. So I'm going to leave X3 at 0, decrease X1 all the way down, and then see what happens to the other ones. So I'd have to start with the first equation. If X1 and 3 are both 0, X4 is 4. And then if X3 is 0 and X4 is 4, X2 will be 6. And so this is another corner, 0, 6, 0, 4. Just like my first one, that's a corner, find the cost at that corner is 6 plus 4, 10. That's my minimum. The opposite thing for the maximum, where I saw the cost go up, start heading in that direction.
Don't you have to keep checking though, to make sure that that's not just one lower than the other corner? Don't you have to check like every corner?
Yeah, you would want to check until you're no longer getting anything that would be keep going down. In this case, none of the other ones are going to go down any farther, but yeah, you would kind of look and see, is there any way I could go down? I guess we already know that like increasing X3 was not working and stuff. So you would have to kind of double check to make sure there are not ways to make it go down further. Sure, yeah. And in this case, there's not. We've kind of gone the direction that we have to go. But yeah, you kind of try and narrow down by just increasing and decreasing points. This still is not super efficient. The large one, there's still a lot of checking to do. But the simplex method is a much more complicated way of solving conceptually, but it narrows it down very quickly so that you don't have to check quite as many things. But we're not going to do huge ones, so we're not going to have to worry about that. Okay. Yeah, tomorrow is a short